When a modern fighter jet violently banks upward, intense physical forces turn the pilot's own body mass into a lethal weapon against their internal organs. The immediate biological threat in this extreme environment is G-force-induced loss of consciousness, known in aerospace medicine as G-LOC. Under extreme acceleration, strict Newtonian physics dictate that centrifugal force acts powerfully on the vascular system, pulling fluids in the exact opposite direction. Here, a human cardiovascular system fails under a 9G load. Blood drains rapidly, pooling in the lower extremities and starving the brain until it goes dark. To counteract this, inflatable G-suits mechanically clamp down on the legs, forcefully squeezing blood back up into the chest. These compression garments offer a strictly limited window of protection, operating as a temporary mechanical stopgap against sustained physical forces. If an aircraft sustains anything beyond 9 Gs for more than a few seconds, standard human cardiovascular resistance fails entirely, regardless of external compression. While aerodynamics may allow for tighter turns and higher velocities, the human circulatory system hits a hard physical ceiling at these speeds. The flight envelopes described in ancient Indian epics involve instantaneous directional shifts. Calculating the centripetal acceleration required to bank at these hypersonic speeds produces G-loads heavily exceeding 9 Gs. To survive these forces, texts describe a distinct primary life support mechanism. Operators sealed deep within the inner sanctums of the craft, surrounded by purified liquids. By cross-referencing these ancient textual details with modern aerospace physiology, we find blueprints for automated life support ecosystems. These systems were specifically engineered to bypass the exact biological failure states of hypersonic flight. Stripping away the outer hull of a Vimana reveals a sealed liquid chamber at the core. The operating principle addresses the bedrock axiom of high-G survival. You cannot outtrain physics. To survive sustained acceleration, the biological frame must be completely insulated. In theoretical aerospace engineering, this concept is known as a hydrostatic inertial dampener. This exact physical framework maps directly to the continuous textual references of rasas, or purified liquids, surrounding the operator during cosmic journeys in the Vimanas. This cross-section compares an air-filled cockpit to a fluid-filled pod. When a 9G vector hits, the atmospheric cabin heavily distorts. In the pod, liquid instantly equalizes the vector arrows. This compressive force matches internal vascular pressure, mechanically forcing blood evenly to the brain. The fluid exerts a uniform pressure across the dermal layer, preventing downward blood pooling. Achieving this precise equalization requires displacing the exact mass of the human pilot with hundreds of gallons of calibrated liquid, perfectly matching human body density. Housing this violently shifting, high-pressure fluid dynamic demands a reinforced cylindrical chamber. A standard angular structure would rupture under the sheer force of the shifting liquid mass. The chemical purity of the rasas ensures stable viscosity. It prevents biological contamination and microbial growth from degrading the dampening effect during extended cosmic journeys. Modern aerospace researchers are only now actively experimenting with replicating these exact liquid immersion suits to protect pilots in next-generation combat platforms. Suspended inside this ancient inertial dampener, the Vimana pilot could execute sustained terminal velocity banks with zero physiological awareness of the lethal G-loads occurring outside. The inclusion of races operates as the physics-based prerequisite for surviving hypersonic inertia. Placing a human in a highly pressurized fluid bath introduces a secondary engineering problem. Managing vitals under these conditions requires continuous, instantaneous response mechanisms. The ancient physiological science of Ayurveda features an intricate mapping of the pulse, known as the nadi, correlating rhythmic fluctuations directly to internal oxygen flow and bodily stress. The texts outline a biomechanical interface, metallic cuffs tightly wrapped around the pulse points of the pilot's wrist, feeding physical data continuously into the craft's analog computers. These mechanical cuffs operate as a real-time biometric telemetry system. Constantly reading the nadi, the ship accurately monitors the pilot's exact fluctuations in blood pressure and oxygenation. This creates an automated feedback loop. The Vimana uses pulse data to autonomously adjust cabin pressure and tweak fluid density seconds before the pilot's vitals indicate impending blackout. Processing survival at Mach speeds requires an autonomous, closed-loop response operating in milliseconds. As the Vimana accelerates rapidly past 30,000 feet, atmospheric temperatures plummet well below freezing in seconds, posing an immediate, lethal threat to any uninsulated vehicle. At this altitude, ambient oxygen levels drop completely below human survival thresholds. Without supplemental oxygen, the timeline of hypoxia is merciless. Within seconds, extreme oxygen deprivation severely compromises the central nervous system. The pilot immediately loses the fine motor skills and complex cognitive functions required to operate the mechanical systems of a flying machine. Texts like the Samarangana Sutradhara address this directly, detailing the continuous generation of pranavayu. Delivering this vital air to a pilot submerged in a liquid inertial dampener requires a dedicated, heavy-duty mechanical apparatus. The pranavayu functions as a closed-cycle chemical oxygen generation system, synthesizing breathable air. The pilot relies on a highly pressurized mask. This ensures the generated oxygen is forcefully pushed into the lungs, compensating for critically low ambient pressure. Securing this system involves engineering heavy airtight seals around the breathing hoses, protecting the active oxygen supply from the surrounding high-density fluid dampener. Simultaneously, the onboard vats must continuously scrub carbon dioxide out of the closed loop, preventing the pilot's own exhalations from poisoning the air supply. Continuous high-pressure oxygenation is the direct biological mechanism that keeps the pilot's brain functioning efficiently enough to monitor the ship's analog weapon systems. Without this artificial atmosphere, the highly advanced biometric telemetry and fluid equalization systems are entirely useless. A brain-dead pilot cannot steer. This degree of isolation and pressure management meets the technical criteria for a spacecraft. This CAD-style wireframe models the fully integrated Vimana ecosystem, mapping exactly how these three primary life support components function simultaneously. The data pathways map a precise operational sequence. The Nadi telemetry actively regulates the flow of both the rasas and the pranavayu in real time. A failure in any single node, a sudden drop in fluid pressure, a misread pulse, or a stalled oxygen generation vat results in immediate catastrophic biological failure. The architecture relies on an interlocking chain of physics. High G maneuverability necessitates hydrostatic dampening. Hydrostatic dampening necessitates precision telemetry. And operating both requires closed-loop chemical oxygenation. Together, these systems perfectly stabilize the vehicle, allowing it to execute a flawless high-G ascent straight into the thin upper atmosphere. By strictly applying the parameters as aerospace physiology, we see that these ancient texts detail brilliant, interconnected engineering solutions built to overcome the absolute limits of human biology.